Welcome to Chapter 14 and our first section of Chapter 14, Section 14.1, introducing the concept of functions of several variables. So we have talked in algebra and calculus, everything leading up to this course in terms of functions of one variable, right? Y is a function of x, y equals f of x. But now that we're working in higher dimensions, as we saw in the previous chapters, we need to kind of up the stakes a little bit. We need to introduce functions of more variables so we can describe more types of objects. So given a function of two variables, we're going to have z is a function of x and y. So z equals f of xy. We have still a domain and a range. So the domain is every ordered pair of real numbers, x, y, in a set D. And the range is the set of values that f takes on for each of those ordered pairs. So back in algebra and Calc 1 and Calc 2, we saw that every domain was a set of x values and the range was a set of y values. Here in Calc 3, in the third dimension, we're working with two elements of the domain, x and y, and still one element of the range, that would be the z, or the f of xy. So in this case, x and y are both independent variables, and z is a dependent variable. So x and y are both independent, and so they are not dependent on each other anymore, right? X does not give us y. X and y both give us z. So z is dependent on both x and y. So a couple examples of some functions down here. For part A, we have this function, f of xy is the square root of x plus y plus 1 over x minus 1. When we're looking for the domain of a function, this process remains unchanged from, say, algebra. To find the values in the domain, we want to try to find values that are restricted, that cannot be in the domain, and then we get to say basically that the domain is everything except those. So in this situation, we're going to have, so the domain is going to be a set of all ordered pairs xy such that we have up on top here this function inside the square root. Anything inside a square root cannot be negative, so x plus y plus 1 must be greater than or equal to 0. And this is a rational function, and a rational function with a function in the denominator cannot have a denominator that is equal to 0, meaning that x cannot be equal to 1. So this would be the domain of this function. So it is all ordered pairs x and y that satisfy these rules or these conditions. So x plus y plus 1 must be greater than or equal to 0, and x cannot be equal to 1. If we wanted to visualize this graphically, just put a little graph right here. We would sketch, this gives us a line. We would sketch the line somewhere kind of down here. And then this one would give us a vertical line, but because it's not equal to, we need to exclude it. So x equals 1 would be right about here. So the domain is x plus y plus 1 greater than or equal to 0. So if we look at what side of this line that would fall on, it would be up here. Okay, so this is kind of like exercises you would do in an algebra class. So we put everything above this line or equal to it And then we skip over the specific values when x is 1. And we get everything else up here. Of course, extending off in all these directions as we go out. Then when it comes to finding the function value, f of 3, 2, we handle the substitution of values the same way that we do for functions of one variable. We just sub in the appropriate value in the appropriate places. So we get the square root of 3 plus 2 plus 1 over 3 minus 1. So that's the square root of 6 over 2. So that would be the function's output. That would be the z value, if you will, right, or the f of 3, 2 value. Then for part B, so looking at the domain first, it's going to be the set of points x, y. And if we look at restrictions, the x in front has no restrictions attached to it. But the fact that we have a natural log here of y squared minus x definitely introduces a restriction, because anything inside of the natural log must be strictly greater than 0. So y squared minus x must be greater than 0. If we go ahead and just like move the x to the other side, that tells us y squared must be greater than x. And that's our only condition. So as long as this condition is satisfied, then we have a valid input for this function of two variables. So again, if we were to look at its graph, x and y, if we were to look at x equals y squared, so the curve itself, that would give us a sideways opening parabola, although because it's not strictly, it is strictly inequality here, we would go ahead and just dot it or dash it so that we make sure not to actually include the curve. And then the inequality tells us, so like if we picked a point like in here, if x is like 1 and y is 0, that doesn't satisfy this inequality. But if we pick a point like up here or down here, it does. So if we pick like x is 0 and y is 1, that does satisfy it. So all of the points in the domain are the ones out here. So everything kind of outside this curve falls into the domain of this function. And then substituting in, of course, we get the same kind of thing here. So we're going to get 3 ln of 2 squared minus 3. That's 3 ln of 4 minus 3 is 1. ln of 1 is 0. So we just get a 0. So let's take a look at a similar one. Find the domain and range for this function. We have the square root of 9 minus x squared minus y squared. So for our domain, it's going to be a set of points x, y, so a set of ordered pairs, such that everything inside here has to be greater than or equal to 0, right? Because it's inside a square root. So we have 9 minus x squared minus y squared must be greater than or equal to 0. So if we rewrite this a little bit, so we're going to have the domain, it's the set of points x, y. Let's go ahead and put the variables over to this side. That'll make them positive, and it'll get them away from the constant. So, and let's go ahead and kind of flip this around a little bit. So this is going to be x squared plus y squared. So I moved these, added them over here, but then I'm flipping it so that the variables come first. So they're going to be on the less than or equal to side of 9. So this would be our domain. So it's all ordered pairs such that x squared plus y squared is less than or equal to 9. And then the range is going to be a set of z values such that z equals the square root of 9 minus x squared minus y squared, with x and y being elements of the domain. So it's basically just kind of restating the rule of our function. Okay, so the elements of the range will be all the outputs of this function given an input that is in the proper domain. So if we look at what this means for our z values, again, we know that the output of this square root function cannot be less than 0, right? It can't be negative. So that means our z is going to have to be greater than or equal to 0. And if we want to look at like an upper bound on the range to see like what is the largest that it could be, well, this gets the smallest when x and y add up to 9, right? If they added up to be equal to 9, then that would make this a 0, and that's as small as it could possibly get, right? That's this one right here. But if we want this to get as big as possible, if we let x and y shrink down to like 0, so then these are gone. If they turn into 0, we're left with the square root of 9, which is 3. If we let x and y go negative, they would still get squared, and then they would be made positive again, and then get subtracted off again. So whether x and y are positive or negative, it's still going to get subtracted off and made smaller, which means that the largest we can possibly make this is when x and y are both 0, and the result is the square root of 9, which is 3. So the square root of 9 minus x squared minus y squared must be less than or equal to 3. So this gives us an updated range here, a little more specific range. So it's all z values such that they must be greater than or equal to 0, but they must be less than or equal to 3. So z is between 0 and 3. Or if you prefer interval notation, we have inclusive of 0, inclusive of 3, that interval from 0 to 3. Right? So there we have the domain and the range of that function. And we're going to come back to this function a couple of times to look and see kind of what it looks like a little more in detail. So we will get to that. But for now, we have our domain and range. Okay. So what I have here is kind of an arbitrary, just general surface that we're going to use to kind of talk about some of these main ideas. So the graph of a function of two variables is a set of all points x, y, z is an element of R3. So R3, like the third dimension. So we have ordered triples here, not ordered pairs, such that z equals f of xy, and xy are in the domain. And like I said, this is called a surface. So you can see over here, the surface is the one in blue. The domain is all of the possible inputs, okay, in the xy plane that when you plug them into the function, it plots a point on the surface. So you can see down here, we have xy 0, okay, so all the xy values get taken from here. We run them through the function, and in doing so, it gives them a height. And that height plots them right here on the surface. So that's x, y, f of xy, or xyz, if we go with that notation. So this is how surfaces are represented. So using functions of two variables, okay, so two inputs, one output. Let's take a look at an example. Sketch the graph of f of xy equals 6 minus 3x minus 2y. So if we go ahead and just replace this with our z notation that we're a little more familiar with, we get z equals 6 minus 3x minus 2y. And let's add the variables over to the other side. So we're going to get 3x plus 2y plus z equals 6. And this type of equation is actually one that we've worked with before. So this is the equation of a plane. And when it comes to graphing planes, the best approach for sketching a surface like this is going to be by plotting the intercepts. Because the plane extends infinitely in all directions, so drawing random points out in space isn't necessarily the most effective technique. We want to have a little more kind of direction than that. So we're going to go ahead and, so again, graph the intercepts. So that means when we're on the x-axis, that's when y and z are both 0. So we would have 3x plus 0 equals 6. So that would give us x is 2. So right there. So that's the point 2, 0, 0. For a y-intercept, that's when x and z are 0. So we get 0 plus 2y plus 0 equals 6. So y is 3. So that's right there. So again, that's 0, 3, 0. And on the z-axis, that's again where x and y are 0. So we have right there, which gives us z equals 6. So we go up 2, 3, 4, 5, 6 to right there. That's the point 0, 0, 6. And we go ahead and connect the dots. Oops. Okay. And then I'll just put a little perspective on this. So this is one piece of the plane. The part that is particularly in the first octant, so it's where x is positive, y is positive, and z is positive. Out here, of course, the plane does extend infinitely in all directions, but this gives us an idea of where it is in space, kind of how it's tilted, what direction it's pointed, those kinds of things, simply by plotting 3 points along the main axes. So a plane, when we look at graphing planar functions in 3D that have kind of this form, like this example. So we have f of xy is ax plus by plus c. These functions, when it comes to surfaces, are considered to be linear functions. Now, we saw in previous sections, of course, that there is plenty of difference between planes and lines. So we're not saying that they're lines. We're just saying in the context of 3D surfaces, planes behave in a linear fashion, right? They don't bend or curve. They go perfectly straight, perfectly flat, just like lines do. In fact, connecting these points, I drew lines in order to connect them. So planes are considered linear in 3D, even though they're not specifically lines. So let's take a look at this next example. So this is the same function that we were working with earlier. So we already found its domain and range, but now we want to actually go ahead and sketch the graph of this. So let's again rewrite this. So we get z equals the square root 9 minus x squared minus y squared. Let's go ahead and square both sides to get rid of that radical. So that's z squared is 9 minus x squared minus y squared. Let's add the variables over. So we get x squared plus y squared plus z squared equals 9. And this is definitely an equation that we know. This is an equation of a sphere. So we have a sphere with center at the origin, so 0, 0, 0, and radius of 3, right? Because 3 squared gives us the 9. But because of the way this is set up in that function notation, if you remember from the domain and range back here, we said that the square root, right, has to be less than or equal to 3, but it also has to be greater than or equal to 0. And when we're talking about the sphere, it shouldn't go from 0 to 3, it should go from negative 3 to 3. But because this one is set up, again, the function itself has a square root, we cannot ignore this. So we need to take that into account. So we can say, but z is greater than or equal to 0. So it is an upper half sphere. Okay, so we're going to still have a radius of 3. So we're going to go something kind of like that. Okay, so here we have the upper half sphere. And if you think back to the domain and range that we found earlier, the domain was x squared plus y squared less than or equal to 9. That is everything inside of the circle of radius 3. So that's the circle down here on the bottom. And the range was from 0 to 3. That's a height of 3 right there. So this does fit. This does track with the information that we found a little bit ago. So this would be a rough sketch of what that surface looks like. This would be an upper half sphere. Let's take a look at another function here. So for this function, find the domain and range and sketch the graph. We have 4x squared plus y squared. So in terms of the domain, we look for any possible restrictions on the domain. There are none. Anything is valid for x and y, right? All real numbers will produce a real number solution. So we can say the domain is all of R2. Okay? And that's an important distinction. It's not just all of R, not just all real numbers. It's all pairs of real numbers because, again, there is an x and a y in the inputs. So don't forget about that. So it's all of R2 is the domain, not just R. In terms of the range, the outputs, well, we know that x squared must be greater than or equal to 0, right? Because it takes negatives and makes them positive. Y squared also is going to make things non-negative. So since x squared is greater than or equal to 0 and y squared is greater than or equal to 0, then our function, h of xy, it must also be greater than or equal to 0, right? Because if they're both 0, it could equal 0, But if it's anything else, it'll go bigger. So this will be greater than or equal to 0. So rewrite this, our range in interval notation will be 0 to infinity, inclusive of 0, exclusive of infinity. Now, in terms of the graph, we can look at this kind of from a few different perspectives here. So we're going to take a look at what happens with x's, what happens with y's, and what happens with z's to get a clearer picture of this surface without just plotting points, because plotting points can be very ineffective in graphing a 3D surface. So let's take a look. First, we'll look when x equals 0 in this formula, and we'll go ahead and relabel h as z. So we're going to get z equals y squared. So this is a parabolic function, right? This is a parabola, but instead of y equals x squared, it's z equals y squared. So y is the input and z is the output. So it's going to be kind of here in the yz plane. So we're going to get something that looks like this, something kind of like that. Okay, and if you kind of drop this down just for the sake of the visual here, it's dropping down to the y-axis right there. If we take a look at when y equals 0, we get something similar. We get z equals 4x squared, which is also parabolic, but it grows 4 times faster than the standard parabola does. So this is going to be in the xz plane, and it's going to go up very quickly. Something like that. Okay, I think that's good enough. And then again, if you want to kind of track this, it just drops down onto those axes. And then if we look when z equals 0, well, when z equals 0, we get 0 equals 4x squared plus y squared, which, if it equals 0, then that's just going to be this point down here where the two sets of curves meet. So let's just look in general. Or actually, no. Let's try picking other values. So z equals 1, for example. We get 1 equals 4x squared plus y squared. If we did z equals 2, we get 2 equals 4x squared plus y squared. These types of graphs, they look like they're circular equations. However, there's an imbalance between the x coefficient and the y coefficient, which makes these actually ellipses, not circles. Ellipses where the radius, well, the radius starts at 0, so that one's not that helpful. But radius of 1, radius of 2, etc., etc., etc. So if we were to draw these ellipses, it's going to stretch in the y direction. So that would be something like, not like that, something sort of like that. Oh, this is not going well, is it? Let me try connecting this one first. Yeah, something like that. And then we go up to the next height, and we're going to get something like that. And we could go up another like that, etc., etc. And you can see instead of plotting points, by just looking at some different aspects of this surface, with respect to x, y, or z, we can get a clearer picture of what this is supposed to look like. The actual graph of this would look kind of like this. And again, this is just a very crude drawing, but this type of surface is called an elliptic paraboloid. So it's a paraboloid because it's parabolic. Okay, so it looks like kind of like a curved cup or like a bowl, but it's not a perfect circle. It's an ellipse in shape, so that's what makes it an elliptic paraboloid. So hopefully that shape is relatively clear over there on the side. So, but this is how we can sketch some surfaces that either we don't quite understand just by looking at them, and we don't necessarily want to just plot point after point after point. Sketching them like this can give us a little more clarity. So moving on to the next major topic for this section, the idea of level curves or contours for a function. So we're talking about level curves or contours. These are curves with the equations f of xy equals k, where k is a constant in the range of f. So we're taking our function, and instead of setting it equal to z, a variable that can change, we set it equal to one constant value, one single number, and we see what type of curve that gives us. So this is the set of all points in the domain of f at which f takes on a given value of k. So this is all points in the domain where f takes on the value of k. So the function output gives us like the height, right? It tells us how far up to go off of the xy plane. So what we're saying is these curves are all points in the domain where the graph of f has a height of k. So I have a visual for us here to take a look at. So you can see over here on the left, I've got the surface in question. And what I did was I noted different values of heights on the surface. So this height, and then I move up to another height, and then another height, and another height. And you can see that the curves up here, they all trace out different heights on this surface. So you can see them move all the way around the surface, all the way up to this point right here, right at the tippy top. That gives us its own height value. What we did was we took these curves that are equal to k values. So like the k values would each represent a different height here. So this would be like, you know, I think on this one, these are all going from like 3 to 4, something like that. So like k equals like 3, k equals 3.25, k equals 3.5 would be the green one, k equals 3.75, and then the point up here would be like k equals 4, something like that. We can take these curves that are equal to these particular values, these heights, and just drop them down into the xy plane. So you can see each of the curves here, and I've color coordinated for the sake of ease. But you can see each curve up here corresponds to one down here, and I have the flat version of it over here on the right. So this is a contour map, okay, or a set of level curves that corresponds to this surface. And the idea is we don't want to have to always be graphing in 3D like this. We want to be able to use a contour map to understand what's happening in 3D without actually drawing it in 3D. Okay, so we want to be able to read one of these to get an idea of what's happening with one of those. So when it comes to reading the contour map itself, you can see obviously these ones are all concentric ellipses for a shape like this. The important thing to take note of in particular is the distances between them and how that represents changes in height. So for this contour map, you can see from the k equals 3 curve to the k equals 3.25 curve, there's about this much of a tiny gap in between them. And then we move to the k equals 3.5 curve, and you can see it's a bigger gap between those two. K equals 3.75, and we have an even bigger gap. Oh, did I miss one? Oh, I did miss one, didn't I? Yeah, so we'll say that purple is k equals 4, and then we'll say that this is k equals 4.25. Something like that. These are all just estimates. It's meant to be completely arbitrary. So this would be k equals 4. So we've got this big gap, and then k equals 4.25. It's this little point right here, and you can see the gap is getting even bigger as we go inward. The distance between these curves represents how far the surface traveled before it made a change in height of 0.25. So if the curve goes from 3 to 3.25 and only this tiny little distance, that means the curve is very steep, so it grows very quickly, very sharply. Whereas like this one, this is the same height difference, right? It's only 0.25 height difference, just like these two are. But this one, it took this long for it to go from 4 to 4.25, whereas it only took this one, this teeny tiny little distance, to go from 3 to 3.25. So that means this is very steep, this is very shallow or very flat. And this is one thing that we can read from contour maps. So you can see that these values are getting more shallow as we go up the surface, right? Because all of these are changing by the same height, but over much wider ranges as we carry forward. And if we look back at the surface itself, of course, that tracks, right? Because you can see this height difference here is very quick. It's very steep. But then we start kind of leveling off a bit until we get to the top where it's totally flattens out up here at the top. So we can see the decrease in that slope, right, in that incline as we go, and that's represented here in the contour map in those level curves. So the closer the contours are together, the steeper the surface. Okay, so closer the contours, steeper the surface. Okay. And by the same token, the wider the contours get, the more shallow, okay, or flat the surface is. Some common examples where you can see contour maps, like in the real world, in application, are topographical maps and weather maps. These are two very common locations of contour maps and level curves, and I have a few examples here to show you all. So here we have a contour map. So you can see some mountains on here. We got Mount Marcy, it looks like. Mount Haystack over here. But if you look at the level curves, you can see for this mountain, for example, for Mount Marcy. So the top is right here. If I was going to hike up this mountain, going this direction and going this direction, it's the same height, right, to get to the top. However, if we look at the level curves over one path or another, you see how tightly grouped these level curves are in here, right? The distance between them is incredibly small. Each one of those represents an elevation change. That elevation change is exactly the same as these elevation changes, because each contour represents a different height. So, and you can see here, right, this one is 1400. We've got 1225 is on this contour down over here. Got 1450 is this contour. So it looks like they're going up by about 50s in these big groupings. So each one of these would be about 10 feet in elevation. So going from like here to here would be about 100 feet. Whereas going from here to here would be the same 100 feet. But you can see this distance is significantly smaller than this one. So when it comes to kind of interpreting it for the mountain side, this side would be like a cliff, and this would be a much smoother, easier hike up the mountain. So if I was going to hike up the mountain, I would want to come at it from this side, not this side. And if you look, there's a little path right here. That would be a trail. And notice the trail kind of follows along the path here, and it kind of cuts through these wider contours, right? All the way through here. It cuts through the widest parts of the contours. Same thing like this mountain over here. Seems very, very steep, right? Because these contours are so tightly grouped together on both sides. Here, it gets a little flatter at the top when you reach the peak, but not a lot. So let's look at another one. So this gives you a little bit of a clearer idea, I think, with these labels. So you can see the tighter the contours, the steeper the terrain. And of course, the wider the contours, the flatter the terrain. Let's see. This is the one that I want to take a little more time with here. So if we look at this map, so you can see where the ranger station is down here. You can see like the parking lot, the visitor center over here, and you can see in this general vicinity, not a lot of contours, right? And they're very wide, very spread out contours, which is why they built all this stuff there, because it's relatively flat. But as soon as we go away from the center, so just past like the amphitheater out here, we go down over towards the spring down here, we go across over this way, you can see it's growing much steeper out there on the outskirts. And one thing I wanted to point out about this, when we look at some of like the roads and the trails and such, so like this out here, notice that as much as possible, this trail or this road is hugging the contours as much as it can, right? So we're not just like cutting straight across, right? We're not just driving right across the top like this, because in terms of viability, that's not very easy to construct, because then your road would be going like this, up and down the different heights of the mountain. So what they do when they create these trails is they want to stick with the same contour as long as they possibly can, because that means the least amount of elevation change, so that's the easiest on the hikers or the drivers or what have you. So like same thing, this one branches off here. You can see it cuts across the contours here, but then once we get up here, so you can see it's kind of doubling back and forth a little bit, right, and winding to fit the contours as much as it can. So contour maps, level curves, give us a good sense of elevation changes, height differences, all of that kind of stuff. So one last one, we have a weather map here, and you can see all the different values, and you can see each one representing like areas of high pressure, low pressure, and how rapidly or gradually that pressure is changing as we go around the map. So lots of different uses for contour maps and level curves. So let's go ahead and take a look at one, a little practice reading one here. Use the given contour map to estimate the values of f of 1, 3 and f of 4, 5. So we're going to look for estimates here. So we find the point 1, 3. So that's 1, 3 is right here. Now this value does not lie on a contour. It lies between this contour and this one. So we need to estimate. So this contour is 70. This one is 80. So it's between 70 and 80. It looks to be a little bit closer to 70 than it is to 80. I would say somewhere in the maybe 72, 73 range, somewhere in there. So this height would be about 73. And as long as we're anywhere in that ballpark, that's fine. And then the other one, f of 4, 5. So we go up here. We're between the 50 contour and the 60 contour. It looks like maybe slightly closer to 60. So we'll say maybe like 56, like just a little bit more than halfway to 60 from 50. Okay. So we can read things like height. We can read things like slope, the steepness, right? The slope is going to be much steeper in these sections, right? And much more shallow in these sections where we're kind of going wide distances between the contours. Let's try actually graphing a little bit. Sketch the level curves of the function 6 minus 3x minus 2y for these different k values. So for our level curves, we're going to take the function and set it equal to k. And we're going to get these different values of k. Now, in terms of the equation that we get out of this, if I go ahead and let me add this over here and subtract that over there, so kind of just flip-flop them a little bit. So we have 2y equals negative 3x plus 6 minus k. And let me divide away the 2. So y equals negative 3 halves x plus, that would be 3 minus k over 2. If we look at what this equation produces, if we kind of just imagine that we're grouping these two together, this has the form y equals mx plus b. So this would be a linear equation. Now, what the line is specifically depends on what this value of k is, right? So as k changes, we'll get different lines, but we know that we will get lines. So this is going to be a family of lines, okay, and they'll all be parallel because they all have the same slope. So let me actually say that here. So it's a family of parallel lines with slope m equals negative 3 over 2. So move this over a little bit. Oops. Okay. So if we start subbing in some of these k values, we get y equals negative 3/2 x plus 3 minus negative 6/2. So that's a negative 3. So we end up getting negative 3/2 x. That's 3 plus 3, so plus 6. So we're going to have a y-intercept of 6 up there. And we go down 3/2, down 3/2. And then we try to connect the dots as best we can. Okay, so that was k equals negative 6. If we do k equals 0, y equals negative 3/2 x plus 3 minus 0, so just plus 3. So it's basically the same line, just shifted down 3 units. So let me see if I can actually just... Nope, that was not what I wanted to copy and paste. So we're going to have the same line, just shifted down 3 units. If we go k equals 6, y equals negative 3/2 x, that's going to be, so plus 3 minus 3, so just plus 0. So we don't even need to include that. So again, it's going to be the same line with a y-intercept of 0, if I can get that there. There we go. And then lastly, when k equals 12, that's going to give us 12/2 is 6. 3 minus 6 is negative 3. So we get y equals negative 3/2 x minus 3. So we get the same line, shifted down another 3 units, right about there. And I'll actually move this up a little bit. Close enough. So as you can see, our level curves here are going to be this family of parallel lines. But not only are they parallel lines, but these are equally spaced parallel lines. So notice that the values of k were all equally spaced, and then the lines themselves were also equally spaced. This is not necessarily going to happen all the time, but this does give us information about this curve. As a matter of fact that it's all equally spaced means that it's not growing faster or slower at any particular height, right? If these were all very closely, so if we went from like really wide to really thin like this type of contour map would mean we have gradual and then rapid growth, something like this. But in this case, we have evenly spaced lines, meaning that the growth is steady the entire way up. And that is something that we have worked with. And actually, this equation is one that we have worked with before too. This was the equation of the plane that we worked with a little while ago that we graphed. Remember, we plotted 2, 0, 0, 0, 3, 0, and 0, 0, 6, like up on the z-axis. So We have worked with this plane before, and this is, again, planes are considered linear surfaces, and this is why, because their contour maps are lines. They are equally spaced parallel lines. Now, if you picked contours that were not equally spaced, like if I had picked -6, 0, 6, and 7 instead of 12, that 7 contour would be really close, but the contours were not picked evenly spaced. So we just need to be mindful of that to get the pattern down. So let's take a look at something a little different. So we're sticking with the functions that we started with today. We have the function, the square root. So we found that this was a sphere earlier, right? So if we take this, set it equal to k, for k equals 0, 1, 2, and 3. So we square that. That's going to be 9 minus x squared minus y squared equals k squared. And let's move some things around here to get the circle equation. So that's that. Move that over here. So we're going to get x squared plus y squared equals 9 minus k squared. This equation, just this part of it, tells us that it is a circle. So these are circles centered at the origin, so at 0, 0. And the radius value is going to be the square root of whatever this number is. So if we look for these different k values, so k equals 0, we get x squared plus y squared equals 9. So that's a circle of radius 3. Okay. And then I'll color coordinate here. K is 1. We get x squared plus y squared equals 9 minus 1. So 8. So square root of 8 is going to be 2 rad 2. So it's between 2 and 3, but it's a little closer to 3. So that's going to be something kind of like that. Then 2k equals 2. So that's going to be x squared plus y squared equals 9 minus 2 squared is 4. So we're going to get 5. And again, the radius is radical 5, which is between 2 and 3, but this one is closer to 2. So it's going to be hugging pretty close to these values. Something like that. And then lastly, when k is 3, we get x squared plus y squared equals 9 minus 9, so 0. So that's just going to be that point right there. Okay, so we have k equals 0 out here. K equals 1, k equals 2, and k equals 3 right there. So this would be our contour map, our set of level curves for the sphere. And if you picture again what the sphere looks like in 3D, it's very steep at the edge and very flat as we get towards the middle, right? It kind of goes like this. So like right here, this is very steep. It's pointed almost straight up. That's this value over here. But when you get towards the top, it starts flattening more and getting, right, a little bit wider there. So this does track with what we know about the equation of a sphere and the graph of a sphere. So those would be the level curves. There's one more example here that I went ahead and already kind of filled this one in, just so you guys can have a frame of reference. We've got that same style of elliptic paraboloid here, just +1. You can see the contour map is all ellipses, and the surface, you can see the contours around it, and then how it projects down to the contour map down here. So you can see how that would be created. Now, we're going to be spending most of our time in functions of two variables, so like z is a function of x and y, but we can look at higher dimensional objects as well, at least minimally. So a function of two variables that we've been working with maps to a three-dimensional surface. Similarly, a function of three variables maps to a four-dimensional surface. So we up the number of variables, we up the dimension. Now, what we've been doing is we've been taking 3D surfaces and projecting them down to get 2D graphs, right? And we can read the 2D graph to get information about the 3D graph. This can be useful when working with three variables to 4 dimensions, because I can't visualize what a 4-dimensional surface looks like, but I can project it down, just like this one. We went from 3D to 2D. We can project 4D back down to 3D again, and we can visualize it that way. So the projections down 1 dimension for 4D are called level surfaces. So instead of level curves, we have level surfaces. So like, for example, if we have this function of 3 variables, x squared plus y squared equals z squared, this is a 4-dimensional object, okay, a 4-dimensional surface, because technically it's got 3 variables in here, and then a 4th one is the output, right? So 3 inputs, 1 output. But if we take the level surfaces, we set this equal to a constant, say k. This is an equation that we know, right? This is an equation of a sphere. And it would be concentric spheres, and they would look something like this. Now, pretend that these are filled in. I opened them up so that we could see all the spheres inside. So you can see I've got a sphere in here that would be like k equals 1. The orange one would give us k equals 2. This one k equals 3, and then et cetera, et cetera, et cetera. So these are not the surface, because again, the surface is in 4D and we can't visualize it. But we can look at its behavior using this 3D mapping, this 3D set of surfaces, like we did back here with 3D being projected down to 2D curves. Okay, so we're not going to be spending a lot of time with level surfaces. That's a bit beyond the scope of what we're doing for this class. But just so that you can see that the applications of these level curves and level surfaces do go beyond just the 3rd dimension, and we can use them to make conclusions about higher dimensional objects as well. But that brings us to the end of section 14.1. That's our introduction to functions of multiple variables and level curves. As we continue through the chapter, we're going to start developing more of the calculus of functions of two variables, and we're going to see what that looks like as we continue on. So that is it for this section.